another approach to solve the example 2 in Simulink actually. To use Simulink, we going to define the whole right hand side term as a new variable u, and here, because in Simulink we could find this function, the input function, for example, the integration, the step, and the sign in Simulink, right? So therefore we don't need to perform Laplace transform for them. So this is the good thing when we use Simulink. So therefore after that we could similarly perform Laplace transform and for the derivative terms here. So here this one is second, right, square. This one we have s here, right? Then we put s square, ys, 3s, ys, right, and then 2ys, and then us. And then we could get the coefficient term for ys, and then get transfer function. So this transfer function. So in Simulink, what we're going to do is this one is transfer function. So what we're going to do is we input the transfer function, and then we find the signal. So we find all the signals, the input signals, and in the Simulink, and then as the input of transfer function, and then we could, based on the Simulink, we could predict the output of the transfer function. Actually, is the ys. Actually, in the time domain is yt. Right. Now I want to show you how to get the transfer function, and then how to get the input signals, and then how to link them together, and then to get the output profile. And then I'm going to compare the result we have, and in this example, and with the result we have, and from example 2, to see, and these two approaches can get the same result. Okay. So to get the transfer function, so you're going to go to the continuous category, and then this transfer function, right? Transfer function term. Okay, now I want to show you. So we go to the Simulink window here, and then so you have your new Simulink, right? And then you're going to save it. And the name of this and Simulink is example and 3 Simulink. Okay, and then now I want to show you how to add the transfer function. Right, the transfer function here, we want to add transfer function, and this is the transfer function we're going to add. Right, so I want to show you. So we go to the library. This is the library of Simulink, and then you're going to see this library of Simulink. Then you're going to get the continuous, right? And then you could see transfer function here. Just draw it here. So I zoom in a little bit, and then you just double click. Okay, and then you type here the coefficient here. So the coefficient is from the high orders to the low orders. Yes, from so for example, this numerator is coefficient is 1, for the denominator is 1, 3, 2. So from higher order to lower order. Okay, so we just type this in, right? So here the numerator coefficient is 1, the denominator is 1 and 3 and 2. Then just click OK. That's it. Okay. So we get the transfer function, and then the next step is to add we're going to add the three input terms here, right? The three input terms. The first one is the integration, and then the another two is the step and the sign, right? So to get the integration term here, so here, so I write the integration term here is e exponential minus tau d tau 0 to t, right? So we could think that this is the tau, the terms actually here the thing as the term t. Okay, and then you can see we could find a function exponential here, this function exponential u here, right? Exponential u. So this input is u, output is exponential u. So but in this example, the u is what? This u is minus tau, right? So therefore we're going to, so we need to times the gain here. So tau from the clock is tau times minus 1. So this one is minus tau. Minus tau is the input of the equation of the function of exponential e u, right? So therefore this one is e minus tau, right? Okay, and then this one is the integration. So this one is, after this one you get integration e minus tau. Okay, and then here you have coefficient t here, 2 here, because of we have a 2 here. Okay, right? So now I want to show you how to implement this in MATLAB. So move this around, and so get the time function here. Go to the source clock, right? And then this the tau, and then tau needs to times minus t minus 1, right? So go to the gain to get the, here's the math operation. You get gain here, and then put the gain here, and here double click, you get minus 1. So this minus tau, right? And then right, minus tau is the input of the exponential u, the function, right? So go to the math, and then you could get, see, go to the math operation, you go to get the math function, right? Then you could pick the exponential here, exponential, okay, input, and then the output. The output of the exponential function is the input of the integration, right? So we need to add the integration. Integration is in the continuous here, integrator, right? Link them, okay, and then you need to times 2 because 2 times integration, right? So this is the gain. So you select this one. You could copy it. Just hold the control and use the mouse to draw the game, and then you could copy the game. Right, here's 2. Okay. So this the one. So there's 3 input terms for the trans function, right? So we add this the first one. So we could add the summation sign here. Add, right? So double click, and then we have 3 inputs. So we add 3 plots here, right? So this input of the trans function, and this the first one. So we move this already around. This first one. Good. Save it. Okay. So this is the first one. And then we want to get the second input is the step. So the step here. Get the second input is the step. the step here, and the time delay is just the initial value is 0. The final value is 2, right? The final value is 2. In actually and then the step time is 5. Okay. So for the first one, the integration, you need to set the initial value 0. Okay. So now we work on the step function. So again, go to the source, and then you could get the step function here. Step, show it. Double click. Step time is 0. Step time is 5, right? T minus 5, so 5. Initial value is 0. Final value is 2, because 2 times step t minus 5, right? So this second input, and the last input is sine 3t, right? So we go to here, the source. We're going to sine wave here. Okay, and for the sine wave here, we need to be careful here, because the magnitude here is 1, because the coefficient here is 1, right? 1 times sine 3t, and the frequency here is 3, because here 3. This one is frequency. Okay, so we could double click, and the magnitude is 1, and the bias 0, phase 0, other 0, frequency is 3, and then click OK, and save it again. So we are ready to go, and we're going to save the output. And so we're going to save the output. Use them into the workspace here. Workspace, and save the output as YT2, because we're going to compare with the result we get from example 2, right? Be very careful here. We need to save the format as array. Okay, otherwise you can get when you plug the YT2, you can get the correct result. So here I want to show you. So we want to save the time to T2, output to YT2, and then we're going to save the format as array. Okay, so here's array. Okay, now I'll show you. So we already saved YT2 as array, and then we want to save another one for the time. So here's the time. Save it. This T2 again is in array. Okay, and then that's it. But sometimes you want to debug the program, right? So we also maybe you need to add a scope to see the profile before you plug them. You could use the display and the monitor to display the steady state value. Save it, and then we need to specify the simulation time here. So we go back to the node, and then we can see the simulation time is 100 seconds. Okay, so we change the time to 100. Right, save it. Equals run simulation, and to see what result you're going to get. Okay, so just double click of the scope, and then you can see we get similar result as the one we get from example 1. Okay, now we want to plot the simulation result, because the profile shown in the scope is not that good. So what I'm going to show you here is to type this to type these commands and to plot the profile from the example 1 and then example 2, right, and also from this simulation. So we're going to run the simulation to get the data for T1 and t2 and yt2, and then we use this command to get. We use the program we have developed for example 2 to get the profile of t1 and yt1, and then we plot them together. Okay, so now we run a simulation first. Run simulation, and then we get data for t1 and yt2. Okay, and then we make a new main function. So we save it. We copy the program from example 2 because we want to get profile. We want to get a profile for here. We want to get a profile from example 2, right? So we get the profile from example 2. Right, just save it. So you could just press Ctrl and S and you could save it. Save it as a main function for example 3. Okay. So this line is used to they are used to plot the profile for t1 and yt1 from example 2. Now we need to add, hold on, right, plot t2 yt2, and then here the color here we change to red and plus. It's not continue line. Okay, it's not a solid line, right? And then the line width is 2, right? And then S label. We can copy the S label and Y label from example 2. Okay, just save time. S label, Y label here. There's 2 of them. Just copy it. S label, Y label. Okay, save it. But we also need to get. Oh, we also need to get a legend, right? The legend here. The legend. The first curve is for. Laplace transform approach. The second curve is from simulation approach. Okay, save it. Now you just need to plug it. Just type main example 3. See, you could see here. You can zoom in. You could see the blue color one is a Laplace transform one, and the red color and plus, and represent the result we get from the simulation. They are the same, right? It doesn't matter which one you're going to use, right? But the result is the same. So we are done with examples.